Hello, dear colleagues. My report is the Lorentz microscopy methods for magnetic domain structure study. Present transmission electron microscopy methods allow to solve extensive range of research problems in solid state physics and material science. Lorentz transmission electron microscopy occupy a special place. Lorentz microscopy method allow to obtain direct magnetic domain structure images of thin films, magnetic material. Nowadays, a number of researchers describe both magnetic domain structure study and methodical reports on electron microscopy's adaptation for transmission electron microscopy. Using specifically designed sample holders allow in situ study of magnetic domain structure evolution depending on temperature, external magnetic field, strain, etc. The defocus method is usually used to magnetic domain structure study in which domain walls are observed as light and dark contrast on magnetic domain boundaries. Nevertheless, there is a so-called aperture shift method, including low-angle electron diffraction method, in which magnetic domain are directly observed instead the domain walls. The aperture shift method is the following the electron beam transmission through the magnetized sample along the y-axis. The electron beam is deflected by the Lorentz force along the x-axis. The angle of electron beam deflection by the sample magnetic fields is determined by the expression, where phi is the angle of electron beam direct deflection by Lorentz force along the x-axis. T is sample thickness, E is electron charge, M is electron mass, U is acceleration voltage along the z-axis, and My is the sample magnetization projecting along the y-axis. Since the electron beam deflection has different directions in the adjacent magnetic domains transmitted through the magnetized sample electron beam is split into several parts. This split can be directly observed on the low-angle electron diffraction patterns for both direct and diffracted beams. Aperture can close on the split beams. Alternate domains look like light and dark areas. The dark domains correspond to the beam which is closed by aperture. Both methods in detail and the theory of the magnetic contrast origin are described in 1011 in references. In this report, we described capabilities on conventional transmission electron microscopy Hitachi IT HT 7700. The next picture shows the electron beam is deflected at the opposite direction with divergence angle 2 phi. Is adjacent magnetic domain. Intensity excess is observed in region 1 to strich. Intensity lag is observed in region 2 to strich. When sample image is observed in A to strich B to strich plane under focus condition. Reverse contrast region 1 strich is intensity lag, region 2 strich is intensity excess, is observed in A strich B strich plane over focus condition. The contrast is alternating light and dark bands on the magnetic domain boundaries, so-called domain walls. Domain wall contrast disappear at in focus condition AB plane. It should be noted that the width of the domain wall image is dependent not only the focus distance, but also on the film thickness and the magnetization distribution within the domain wall. The next picture shows magnetic domain images of nickel thin film at our focus A strich B strich plane. See picture on the left. In focus A B plane and under focus A to strich B to strich plane conditions. White and black rows, see fig height, show magnetic domain boundaries where excess collecting domain walls and lack divergent domain walls of intensity are formed respectively. Picture shows that magnetic contrast absent at in focus condition. Picture shows the same rear image of nickel thin film with reverse magnetic contrast A2 strich B2 strich plane. Fig on the left. Next picture shows classic example of vortex magnetic structure formation in iron thin film upon objective lens, external magnetic field application. External magnetic field is perpendicular to the film plane. The vibration on magnetization ripples is clearly visible beside the main domain walls. Vibration is characterized for magnetic film having magnetic anisotropy dispersion, including the normal direction to the film plane. Red rows indicate the magnetic poles, the area in which the magnetization vector perpendicular to the sample plane but opposite in direction. The next picture show magnetic domain structure observation scheme by aperture shift method. Since current supply of main objective lens is switched off, Diffraction image is formed in selective aperture region. Selective aperture used to isolate on the split low angle electron diffraction peaks. This is analogically operation with objective lens aperture in transmission electron microscopy mode. The objective lens aperture used to select the sample region which correspond to the low angle electron diffraction pattern. Minimum aperture size of objective lens Hitachi HT7700 is 10 UM in diameter. Consequently, the sample area size corresponding low angle electron diffraction is about 10 UM. The next slide, number 8 slide, shows magnetic domain image of the iron thin film obtained by defocus method. Low angle electron diffraction pattern insert of early picture allow to determine magnetization direction of adjacent magnetic domains. If zero diffraction peak corresponding unsplit reflex is a long angle electron diffraction pattern was obtained from blank area was superposed with long angle electron diffraction pattern of adjacent magnetic domains. Straight line tangent bar between double diffraction peak mean that domain walls are Bloch walls. Tangent bar have accurate shape if domain walls are Niel walls. However, Niel walls are formed as low film thickness about 100 angstrom. Therefore, deviations are quite small to determine the domain wall type by tangent far shape. For 180-degree magnetic domain, value of local film magnetization possible to determine by distance between double diffraction peak if the film thickness is known and vice versa. Picture shows image of the same film area obtained by aperture shift method. Domain corresponding to the closed beam circled in red on insert on picture has become dark. Magnetic inhomogeneity are visible inside dark domain. In addition, there is an inversion in the phase banded contrast, the nature of which require further study. Other picture shows magnetic domain images of one and the same area of nickel thin film. Image is magnetic domain image obtained by defocus method. The insert shows the corresponding low-angle electron diffraction pattern. The distance between the split diffraction peaks of nickel thin film is 3.5 times less than iron thin film, which is consistent with the published data on the magnetization measurements for iron and nickel 11 and 10 references. Picture are magnetic domain images obtained by aperture shift method and correspond to the close upper and low diffraction peak. See insert in the fig, respectively. Low angle method is most preferred to determine the magnetization vector direction in thin foils and epitaxial films due to lack vibration, which characterized for polycrystalline and amorphous films. We demonstrated capabilities of Hitachi HT7700 for magnetic domain structure study of thin films. The combination of defocus, low-angle electron diffraction, and aperture shift methods can provide full information not only about the size and shape of the magnetic domain as well as the local distribution of the magnetization vector in the film plane. The feature of low-angle electron diffraction method can establish the correlation between domain walls and crystal lattice defect.